Okay, so the next unit is called limits. And we're starting off by looking at limits from graphs. And so limits, we've used this notation before to talk about end behavior, but it doesn't just apply to end behavior. Limits have a really long and complicated definition that we'll look at next year in calculus. But basically, what a limit is the y value that a function approaches as x approaches like some value. So like we were talking about, if you have a function like this, we were saying, oh, the limit of this function as x goes to infinity. So we're saying to ourselves, okay, as x is approaching infinity, going to some value, what is the y value that the function approaches? Oh, that y value is infinity. So that's what we're saying. More grab this. So the way that we read this, bless you. The way that I would say that is the limit of f of x as x approaches a, and a is just some number that we have. So the limit of f of x as x approaches a. And there's some other little things. So notice this one's might be hard to read, but that says a plus. This means this is talking about the limit from the right, or it's also called the right-hand limit. And this one with the negative sign next to it is from the left. And so when it's just the number, that also means it's implied that it's from both sides. Okay, and so again, for limits, limits are all about the y value that a function approaches. Good morning. I should grab one of those. So it's not about the actual y value that we have, it's about the y value that we're approaching. So for number one, we're approaching 3 from the right. So we have this function. As we get really close to 3, as we're approaching it, and we stop at 3, what y value have we approached here? 3. So we came in from the right, and from the right doesn't mean like from like 2 miles away we approach in and then we come here, Approaching really means like, I'll even zoom in for emphasis here. Approaching really means like when we're right here, just to the right of it. If we go left and we're approached from the right, like where are we, basically? So approaching is like right before we do it. So same thing, as we go from the left, we're really starting, like you can start here, down at that point, and then we're approaching from the left. But really it's talking about like right up against that point, what y value are we approaching from the left? 2, exactly. And so what it really just means is, like the right-hand limit is just that y-coordinate, the left-hand limit is this y-coordinate right there. That's the number we're going towards. And it doesn't matter that this top one has an open circle and that we never actually get there. The limit is the number that we're going towards.
So if there's just like 1 point jump, it would be just the same?
Yes, exactly. So this one would be 2, and So for number 3, it's just asking for the limit as we approach 3. That means from both sides. So when both sides are not the same thing, we say that the limit does not exist. You just write D-N-E. The limit does not exist. Shout out Mean Girls. Have you guys seen that movie? Good. Good. Everyone should watch it for more. Yeah. So, it does not exist when the left side and the right side don't match. So, let's look at as x approaches 1. So, here's x equals 1. As we approach from the right and as we approach from the left, and the y coordinate at that spot are all the same thing, right? What is the limit as x approaches 1? 0, yeah. From the right, we're going towards 0. From the left, we're going towards 0. And so when those limits from the left and from the right are the same, then we say that's the limit at that point. Okay, you guys take a look at 7, 8, and 9. Limit as x approaches 2. Okay, what are we thinking for x approaches 2? So 1. For all of them? Yes, that's right. So yeah, when this function is just, it's not broken up at all, it's just a line through there, or another way to say that would be the function is continuous at that point. We come in from the right, we just hit the y value that's there. We come in from the left, we just hit the y value. And so the limit from both sides is 1, and the function, the limit at that point. So a lot of times in a function, it's just the normal y value that's there. So for example, number 10, the limit as x approaches -1, it's just going to be the y value there, which is 0. As x approaches -2, it's just going to be the y value there, because the function's continuous. So it's -1. So where it gets a little crazy is at things such as this. And what is our name for that kind of thing? A jump discontinuity, yeah. So when a function jumps, has a jump discontinuity, that's when the limit is not going to be the same from both sides. And that's when it's going to not just be the y coordinate at that point. It's going to be the y coordinate that we're approaching. So for example, 3 from the right, what are we approaching? 0. And -3 from the left, what are we approaching? 2. Yeah. And so we would say the limit as x approaches -3 from both sides, the end does not exist. The limit always does not exist at a jump discontinuity. Always. The limits from both sides do exist independently, but the limit together from both sides does not exist. The limit from each side does exist. The limit from both sides does not exist. That's how it should be. Okay. Last one here. As x approaches 0 from both sides, what y value are we approaching? 2. From both sides, and so the limit there is just 2. And it doesn't matter that we never get there. It's just the y coordinate that we're approaching.
Will open circles like really ever matter in this like we're approaching?
That is a really good question. Will open circles ever matter with limits? The answer is no. With limits, an open circle is treated just like And that's basically the difference between limits and the actual y value. Yep. Nice. So the limit at a whole always exists. And it's just whatever value, whatever y coordinate that whole has.
What about adding a vertical asymptote?
Okay, at a vertical asymptote, the limit does not exist. Let me go to one real quick that has that. I'm going to have you guys do that one. So on the very back page, I think it's just on the back of this packet here. Yeah, as we go to, let's say as x approaches c, we would say the limit, so that c is just this random y value, or x value that we have. We have two ways that we can answer this. We can say the limit as x approaches c from the left is infinity. We can also say does not exist, because technically infinity is not real. Infinity is not a number. It just means something that goes on forever. So if we're approaching infinity, we're never actually approaching a real number. We're just going for forever. So we could say the limit from the left here is infinity, or we could say does not exist, or we could say infinity comma does not exist, because infinity does not exist. This is actually true in something like this, like y equals x squared. The limit as x approaches infinity of the function x squared, we could say infinity, and that's what we've been saying, but we could also say does not exist, and that would be correct. Because if I think of limit as like a stopping point, if I'm going up for forever, am I ever stopping? No, so there's like no limits to the y values that we get. So infinity does not exist. They actually sometimes do mean the same thing. For the purposes of describing end behavior, we want to say infinity just so that we know which way the function is pointing, but does not exist is also correct. Okay. I want you guys on the front page to do these right here. All right. What did you guys get for the limit of 2 from the right? 2 from the left? So 2 from both sides. If these two are the same, I don't need to look at the graph for the next question. And similarly, if they're different, I also don't need to look at the graph. Okay, for 1 from the right, 1 from the left, -1. Okay, I don't even need to look at the graph. That has to be does not exist. Again, we have a jump discontinuity. It's going to be does not exist at that point. Limit as we approach -1, -2. Yep. Again, technically we should be thinking about coming at it from both sides, but also if we just see that there's a point there that the graph's going towards, that's all it is. The graph is limit as x approaches -2. Does not exist. Yeah. Again, a jump discontinuity always. Somewhere on your paper there, I want you guys to draw this Venn diagram here. So here's the relationship between limits and something being continuous. So if a function is continuous at an x value, meaning no hole or gaps, then the limit will always exist at that point. But the reverse is not true. There are plenty of examples where a limit does exist at an x value, but the function is not continuous at that point. So there's your relationship. And one example of that is a hole. Any kind of hole, right? Limit always exists at a hole. The function is never continuous at a hole, but the limit does exist. Okay. Let's go to the next page. You're not there already. Drawing the axes here. Okay, so looking at this graph, just eyeballing it, what is an x value where the limit does not exist? Like,
where x equals 3.
Where x equals 3, yes, the limit does not exist. We can see there that the left-hand limit is 2, the right-hand limit is -2. They're not going to match. Again, it's a jump discontinuity. That's the easy way to spot it. Jump discontinuity or an asymptote. What about the limit at x equals -3? What would that equal? What would you guys say? -1? -4? So what kind of discontinuity do we have in the graph there? What kind of discontinuity is that? It's a hole. Yeah, it's a hole. Does the limit always exist at a hole, according to what I've told you so far? Yes, it does. So the limit does exist. The limit is -1. It's the y value that we're approaching from both sides. We're approaching the hole in the graph, and it does not matter if that's the y value, the actual y value there. What matters is what we're approaching. We're approaching -1. Now, when I say for number 8 here, f of -3, what does f of -3 mean? It is -4, because what's that asking for? What is f of -3 asking for? The y coordinate. So when we say f of -3, it's asking for what is the literal y coordinate at that point. The limit as we approach -3 is what y coordinate are we going towards, even if we don't actually get there. Number 9, is f continuous at -3? No. What kind of discontinuity do we have? Right, we have a hole, right? So it's not continuous. This right here, these 3 questions combined, this is actually the real definition of continuity, or being continuous. So we kind of gave like an informal definition on Monday, saying like, oh, it's all one piece. There's no breaks or gaps in there, and there's no asymptotes, whatever. The real definition is if the limit as you approach that point is the same as the y coordinate, the actual y coordinate, then the function is continuous. So that's the real definition. Here, the limit is one thing, the actual y coordinate is another, so that means it's not continuous. What could we say for this function here, the limit of f of x as x approaches infinity? We could say does not exist. Does not exist is correct. What would be a more helpful answer for describing? Probably infinity. So just saying it's going up forever. As we go to the left, the limit of f of x as x approaches negative infinity. Again, two ways we can answer. What are they? Yeah, we can say dne and we can say negative infinity. We can say both as well. Both are correct. Saying negative infinity is more descriptive. It's just more helpful. But it's not more correct. Questions on any of these so far?
I actually have a question on date.
Yeah.
I'm just confused. Where's the
Right there. So normally we write f of x, right? So if we have a -3 in there instead, that's the x coordinate.
Oh,
yeah. And f, when we say f of x, what letter do we mean?
Y.
Yeah. So it's saying, what is y at -3? Yeah. You did know that, but now you really know it. Okay. So last thing we're gonna do is you guys go to the next page there. Do these examples using that. All right. Let's check this. What is the domain of f?
You.
Oh, -4.
2, 5. U. 5, 6.
Do you agree?
Could you also do -6 to U to this?
No, because here at -4 we have two open circles, so there's no value for x equals 4 or -4, and then we have a hole at 5, so there's no x value for 5. So complicated domain, not complicated, but just a lot of different pieces. So that's domain. What is the range of f? It is all real numbers, negative infinity to positive infinity. Yes. We got this piece going down for forever, this piece here going up for forever, and this guy there kind of fills in the gaps. Yep. All real numbers. All right. So for these questions, when we're saying f of, what are we looking for? The y coordinate, the actual y coordinate. Yes. So f of -6 is 2. F of -4. F of -4. So it's technically not DNE. DNE makes sense because it's saying like it does not exist. Instead we say undefined. The function is undefined for x equals 4. There's just no x value. F of -2, 2, f of 6, 0. Okay, limit as we approach -4 from the left. -4 from the right. -2. Limit of -2 from the left. -2 from the right. Limit of 2 from the left. DNE, or negative infinity. Yeah, from the left would be negative infinity. Yeah. Limit of 2 from the right. Limit as x approaches 0 from both sides. DNE. Yeah, gotta jump discontinuity there. Limit as x approaches 2 from both sides. Yeah. As x approaches 2. It's infinity and negative. Okay. Is f continuous at -2? No, we got to jump there. Is f continuous at -4? No, also a jump there. Is f continuous at 0? Nope, also a jump there. Is f continuous at 2? Infinite discontinuity there. Is f continuous at 4? Yes, it is. 1, 2, 3. Yeah, just that little part right there. Yep. Is f continuous at 5? Nope, you got a hole there. Okay. That's limits from graphs. Questions? All right. Nice.